Well, after we've talked about geometric vectors or vectors represented geometrically, I mentioned before that we really like to transition to dealing with things algebraically because it's very difficult to be us drawing to add vectors together all of the time. And even after we draw them, we need some kind of way to recognize and a way to represent that vector when the drawing's not convenient. So that's the idea of moving to the component form of a vector. So what we're doing is we're representing directed line segments with components. And this is the simple idea. If you think of a directed line segment, let's just look at this directed line segment here in this blue. We have a beginning and an ending. And so we have a horizontal displacement from the beginning to the ending, and we have a vertical displacement, a horizontal movement and a vertical movement. And those two pieces together will represent the length of the vector. We'll know where to start and where to end. And it also represents the direction because we know where to start and where to end. And so that's what we call the component form. And we look at it using, rather than parentheses here, we use these less than, greater than symbols so that we know that when we're talking about a vector. And the first component is the horizontal displacement, the horizontal movement from the beginning to the ending of the vector. And of course, if the number is positive, we move to the right. If the number is negative, we move to the left in the negative direction. And the second component, the second portion, it's called the second component, represents the vertical displacement from the beginning to the end of the vector. And if that number is positive, then we move up to go from the beginning to the end. If that number is negative, then we go down. And so that's the basic idea. And it's so simple the way we add vectors when we see this is you'll think, man, why'd we do the other? Now, the other thing to be aware of is that we remember a vector can be in any place in the plane. If we have the same, well, sorry for that interruption. What I was speaking of just a moment ago is the idea of what we call a position vector. First, we think of algebraically, a vector algebraically represented, and sometimes that's called the component form of a vector. And separate from that is the position vector, a vector in position. Is really not a different vector. When you hear the terminology position vector, we're thinking of putting that vector so its initial point is at the origin, and then of course we have the vector starting at the origin and ending wherever it ends. And when we think of as a position vector, where if this is the component form, it will end at the point A comma B with parentheses. So there's a relationship between these. It's real easy to see. If we see this, then the position vector is when we graph it to that point. And that's the idea behind that. Well, what we want to do next is actually determine the component form of this position vector, or the component form of a vector. So it says find the position vector of the vector v represented by the directed line segment from point 1 to point 2. And point 1 has the coordinates -1, 2, and point 2 has the coordinates 4, 6. So this is the description of what we do, but that's really just, that's hard to read for beginning math students, what it says to do. And really what it says in a nutshell is we're going to write the components of the vector. That's what we're actually doing. And it tells you how to write those components. Well, let's look down here at this diagram. Point 1 is the point -1, 2, which is this point. And point 2 is the point 4, 6, which is this point. So P1 sub P2 directed line segment starts at P1 and goes to P2. Okay, and so what we want to do is we want to write that in component form, and when we write it in component form, then it's thinking of the vector starting at the origin, but it really doesn't matter. The only thing that's important in component form is to know the horizontal displacement. Remember, the first component represents the horizontal displacement. And so let's look over here and say, okay, well, horizontally, to go from the beginning to the end, we have to move right horizontally 1 unit, 2 units, 3 units, 4 units, 5 units. So horizontally, we're moving 5 units, and we're moving to the right 5 units. So the first component is 5. Now, what do we have to move vertically? 1, 2, 3, 4 units vertically. So the horizontal displacement from the beginning to the ending is 4. Excuse me, the vertical displacement is 4. And whoops, down here, my bad. And so the 4 represents the vertical displacement, and that means up. So this is saying 5 units from the beginning point, 5 units to the right, 4 units up. And so when we do that starting at the origin, 5 units to the right and 4 units up, it actually puts us at the point 5, 4. So the end point, if you will, the end point of the vector, the terminal point, is at the point 5, 4. The vector is listed this way, but it starts at the origin and ends at the end point, the point in the plane 5, 4. Now, what this formula says to do is if you want to calculate the horizontal displacement, if you want to calculate this, then you take the endpoint x value, if you will, and you subtract the beginning point x value. That's the difference. That's the horizontal displacement. So if we take this 4 and subtract this -1, 4 subtract -1 is 5. And remember, these have to do with the horizontal position. So 4 subtract -1 is 5. That's that first component. And that's all that's telling us to do here. Now, to get the second component, the 4, we take the endpoint's second component, second coordinate, and subtract the endpoint, the beginning point, the initial point's second coordinate. 6 minus 2 is 4. And so we could have done that without counting. Let's see, we could have come up with this 5, 4 by just doing the arithmetic. 4 subtract -1, first component, 6 subtract 2, second component. I guess I have nothing else on this page, so let's move to the next page. Okay, so here's on the last page, we saw how to take a directed line segment, vector written as a directed line segment, and converting it into the component form of a vector. That's really what we were doing, the component form of a vector. Now, we're going to start here with just thinking of component forms of vectors, and how do we add and subtract vectors algebraically in the component form, so we don't have to worry about the geometry of it, and we'll find out that it's equivalent. So we're starting out with a couple of vectors, v and w, and vector v has in component form has a first component of a sub 1 and a second component of b sub 1, and vector w in component form has a first component of a sub 2 and a second component of b sub 2. And let's assume we've got a scalar alpha. That's alpha. A scalar, remember, is just a real number. So we're going to talk then, we're going to see below, and we see below here, how we deal with vector addition, subtraction, and scalar multiplication. So if we add two vectors together, we add their first two components to get the first component, and we add their second two components to get the second component. If we're subtracting, likewise, we subtract similar components. And if we're doing scalar multiplication, we take that scalar and we multiply each of the components. So algebraically, it's very simple to do. And as it says here, in a nutshell or in words, to add two vectors, add corresponding components. To subtract two vectors, subtract corresponding components. To do scalar multiplication, multiply the scalar with each component. Now, let's see below here why this is consistent with what we've already done before. And so here's the idea behind it. Okay, and think this way. I'm going to help us get through this picture. We've got this vector v, okay, this vector v right here. And we've got this vector w. So vector v has the components a sub 1 and b sub 1, and that means it stops at the point a sub 1 and b sub 1. Now, what does vector w do? Well, what we're supposed to do, vector w has a horizontal component of a sub 2. So we would have to move horizontally a sub 2 units, and that's what this is illustrating down here. This is the distance a sub 2. So we'd move over a sub 2 units, and vertically we would move b sub 2 units, because that is the vertical component of w is b sub 2. Horizontal component, vertical component. So the vertical component of b sub 2, if w is b sub 2. Well, the distance from here to here is b sub 2, and this is where we are. And so we would go up b sub 2 units, that would put us here. So this a sub 1 units, a sub 2 units this direction for w, and b sub 2 units this direction for w. And so that's our w, and when going from here to here, then we would add those together. So the bottom line is all together, we're moving a sub 1 units for v and a sub 2 units for w, and together we're moving horizontally a sub 1 plus a sub 2. Now, vertically, what are we doing? We're moving up b sub 1 units for v, and then from there we're moving up b sub 2 units to get to the end. And so b plus w has a second component of b sub 1 and b sub 2. That's what this is trying to illustrate. The idea behind this is to try to show you that algebraically and geometrically we get the same result. That's the idea behind this. Now, when we look at scalar multiplication, okay, the idea is this. We're given a vector v, okay, and remember it has a horizontal component of a sub 1 and a vertical component of b sub 1. Here's the a sub 1 idea horizontally, and here's the b sub 1 over here vertically. So this is the vector v. Now, when we multiply that vector by a scalar, okay, it says to multiply each component by that scalar. Well, here's what happens. When we multiply the first component by that scalar, we're making the horizontal displacement alpha times a sub 1, clear out here. And when we multiply that second component, which is b sub 1 by alpha, then it makes it, in this case, it looks like twice as long, doesn't it? And so altogether, to here, this whole distance, maybe it's hard to decide this, but this whole distance, yeah, okay, alpha times the scalar times the vector v, where alpha longer this way and alpha longer this way, and so all together this whole thing's alpha longer. And that's a little harder to see with just these alphas and betas. If we were talking about multiplying by a 2, then we could understand it's twice as far this way and twice as far this way, so altogether this is twice as long. That's a little easier way to think of it. But the idea, once again, is we're trying to illustrate here that the algebraic method of scalar multiplication is equivalent to the geometric thought of scalar multiplication. And so we can trade in the geometry for the algebra. That's really what we're trying to accomplish here. Well, let's assume we believe that they're equivalent. And so let's see how much easier it is now to deal with these operations, okay? And so we're going to start here. We're going to add and subtract a couple of vectors. And so we have the vectors written in component form, okay? We have them written in component form, or sometimes it's called position vector. But remember, it doesn't really matter where they start and where they end, as long as we have this horizontal displacement and this vertical displacement, and likewise here. But now we're not going to draw to add these together. We're just going to do it algebraically, and that's going to be very very easy. So we're going to first on A part add V and W, and on B part we're going to subtract W from V. And so we've already looked at the definition of this. What we do if we add the vector, here's the vector V plus the vector W, and what it tells us to do is add them component-wise. So the new vector will have the first component, the horizontal component, by adding the two horizontal components, 2 and 3. And then the vertical component, the second component, we get by adding the two second components from the two vectors, 3 plus a negative 4. And real quickly, we get the vector 5 comma negative 1. That's all there is to it, and that's simple. And geometrically, it would be equivalent. So this is a lot easier for us to do. Now, if we were subtracting, same idea. It's very simple. We subtract corresponding components. So we subtract the horizontal components, 2 subtract 3, and we subtract the vertical components, 3 subtract negative 4. That's all I've written here. 2 subtract 3 is negative 1. 3 subtract negative 4 is actually a positive 7. So this subtraction ends up giving us the vector first component negative 1, second component 7. Horizontally negative 1, vertically positive 7. Okay, now, so we have down the idea of adding and subtracting vectors and multiplication, doing scalar multiplication, where we can do it algebraically, and I've tried to convince you that it's the same as doing it geometrically. Now, the magnitude of a vector is actually a little easier for us. So the magnitude of a vector geometrically, we just say is the length. And so we'd have to come up with the length, we'd have to use the distance formula. But and this is going to be related to using the distance formula. The idea here is we need to memorize a couple of things. And so I've got a little diagram here to say we've got this vector V, and we'll suppose its components are A sub 1 and B sub 1. Okay, so that means if we start at the origin, then we would end up at the point A sub 1 comma B sub 1, but now this is as a point, and of course as a vector we would use the vector notation, wouldn't we? But the bottom line is we have a horizontal value of A sub 1 and a vertical value of B sub 1, and when we lay that out, then those become legs of a right triangle, where the vector V is actually the hypotenuse, isn't it? And since that's a right triangle, then we know the length of V is the hypotenuse. Well, let's just get up here. It's this distance, and how do we calculate, what do we have the relationship? That is the, I'm ahead of myself, and I apologize for that. How do we calculate the length? Well, what's the relationship between the length of the hypotenuse and the length of the legs? We square the length of the hypotenuse, and that's equal to the sum of the squares of the legs. And so without really showing it, remember, and we talk about the magnitude of a vector, its length, using double absolute value bars here. And in this case, it's the distance from 0, the origin that is, to the point P sub 1, which is the length of this hypotenuse. And so think of this as the hypotenuse, length of the hypotenuse is the square root of the sum of the squares of the legs. And that's because if we had this length squared, it would be A sub 1 squared plus B sub 1 squared. And I feel like I'm messing this up. I guess what I want you to remember is this, and it's because we can think of this vector V as we lay it out geometrically, we can think of it as the hypotenuse of a right triangle with these legs. And that we should be able to figure out then what its length is. In a nutshell, if we're given a vector in component form, like we have here, first component is A sub 1, second is B sub 1, then the magnitude, the length of that vector, the magnitude, is equal to the square root of the first component squared plus the second component squared. That's all there is to it. Okay? So that's what we need to keep in mind, and I'll remind you that over and over as we go through these things. Well, here we're asked to algebraically calculate scalar multiples and magnitude, just algebraically. So this very first, and here are two vectors, v and w, in component form or position vector form. And the first thing we're asked to do is to calculate 3 times v. And as we already saw, if we're multiplying 3 times a vector, we simply just multiply each component by that scalar. And so we'd multiply the 2 by 3 and the 3 by 3. And so 3 times v, or 3v, in component form or position form is the new vector 6, 9. Those are the components. Now, in this case, we're asked to find 2v minus 3w. So we would use scalar multiplication on v to get a 2v, and we'd use scalar multiplication on w to get 3w, and then we would subtract component-wise. So a long-winded way, here's 2 times v minus 3 times w. But 2 times v, we just multiply each component. So we get a 4 and a 6, 2 times 2 and 2 times 3. And then subtract, and this scalar multiplication would multiply each component by 3, 3 times 3 and 3 times negative 4. So we get subtract 9, negative 4. Now to do the subtraction, we simply subtract components. 4 subtract 9 is first component, 6 subtract negative 12 is the second component. Of course, 4 subtract 9 is negative 5, and 6 subtract negative 12 is a positive 18. Now, in our last piece here, we're asked to find the magnitude of v. I kind of got ahead of myself. The magnitude of v. And of course, v is this component form, 2, 3. So the magnitude of v is the magnitude of the vector 2, 3. Well, the magnitude formula, if you will, says, okay, take the square root of the first component squared plus the second component squared. So that's the square root of 2 squared plus 3 squared. Of course, square root of 4 plus 9, which is the square root of 13. So algebraically, it's very simple. Okay, the length, if you will, the magnitude, the length of this vector is the square root of 13 units. So that's what, between 3 and 4 units. Well, after this, we'll pause here and we'll have another video, another slide that will, actually another video, that will begin talking about what are called unit vectors. And a unit vector is a vector that's just 1 unit long. Its magnitude is 1. But they come in handy for a lot of things that we do, and so it's important to maybe think about those separately.